multi-level queuing. Okay, so far all the algorithms that we have seen were using a single ready queue, okay, and selecting the process from that ready queue. But this doesn't have to be that way. Okay, we can have actually multiple queues. We can schedule them differently and so on. So instead of having a just single ready queue, we can have many queues. Okay, this is called multi-level queue idea. So ready queue is partitioned into separate queues so that one queue may include some type of processes, the other queue may include some other type of process. For example, foreground processes, interactive processes may be put into one queue, background processes may be put into another queue. So then what we can do, we can serve the foreground processes with round-robin scheduling because foreground processes are interactive. Response time is very important for them. Okay, minimizing the response time is very important for foreground processes. Therefore, they can be scheduled with round-robin. However, for background processes, that is not very important, the response time. So we can just simply schedule them using FCFS scheduling algorithm. Okay, so this is the good thing with multi-level queuing. You can have separate queues which each queue is served with a different scheduling algorithm, okay? So, however, we have to do also scheduling among the queues, between the queues. So we are doing scheduling inside a queue using round-robin or using FCFS, but we have to also do scheduling among the or between the queues. What it means is this. For some time, we have to serve this queue. For some other time, we have to serve that queue, and so on. All right, so this is scheduling between the queues. So for that, we can use one of two approaches. One approach is using fixed priority scheduling to serve many queues. So that means serve all, for example, from foreground queue, which has higher priority. And if you do not have any process in foreground queue, then start serving the process from the background queue. Usually the foreground queue should have a higher priority than the background queue. So as long as there are jobs in foreground queue, serve them, okay? And when there are no jobs in the foreground queue, then you can go ahead and serve processes from the background queue, okay? So this means that we are applying fixed priority scheduling. The queue that has the higher priority will be served ahead of the queue that has the lower priority, okay? Of course, this can cause, of course, starvation, right? Possibility of starvation exists if you apply this. So if you do not want the process to starve, okay, if there is possibility that the foreground queue will always have some processes in that, then there is a possibility of starvation. In such a case, you can apply the second idea, which is time slicing, okay? Now you can apply scheduling like round-robin among the queues. You can serve one queue for a while, and then another queue for a while, and then again the first queue. So you are serving the queues using round-robin idea. So that means each queue will have a time slice during which you will schedule the process of that queue, and then another queue is served using another time slice, which can be equal or can be different from the time slice of the other queue. Then during that time slice, you serve the process of the other queue. So for example, the foreground process can be served 80% of time, and 20% of time we can serve or schedule the background process, okay? So this is time slicing. In this way, we are not starving the processes in the lower priority queue, okay? So this is multi-level queuing idea. So instead of having just two queues, we can have actually many queues. So for example, we can have a queue for scheduling system processes, another queue for interactive processes, we can have another queue for interactive editing processes, we can have a queue for batch processes and student processes and so on, okay? Here the feature of this algorithm is this. Once a process is assigned to a queue, it is not changed. It remains in that queue, and therefore its priority remains static, okay? But this doesn't have to be that way. So in order to have better flexibility, the idea is to use feedbacks and to enable the process to change the priorities, okay? So multi-level feedback queuing approach does this. A process now can move between the various queues, okay? It doesn't have to be sticked into a single queue, okay? Aging can be implemented in this way, okay? So a process may be staying in one queue, in a lower priority queue, but when you change its queue, that means it is moved to another queue. That queue may have a higher priority. In this way, that means you are increasing its priority. You are applying the aging algorithm where when a process stays in the system, its priority is getting increased, okay? So multi-level feedback queue scheduler will have some parameters whose values should be decided on, of course. How many queues are you going to use? What kind of scheduling algorithm are you going to use for each queue? How are you going to increase the priority of the process? That means what is the rule to change the queue that the process is added into, right? So for a while the process will be in some queue and then it will be changed to another queue depending on something. What is that something? What is the rule? Or sometimes the process can be changed to a lower priority queue. So we have to define the method that is used to determine when the process should be changed into a lower priority queue. That means we are decreasing the priority of the process or demoting the process. We need a method or determine a method to use to determine which queue a process will enter when that process is created initially or needs service. Okay? So this has to be specified. All right? Then we obtain a concrete algorithm as the scheduling algorithm. Otherwise, this is just an idea, this is just an approach, and it has some parameters that has to be specified. And when we specify those parameters, then we have a concrete algorithm, scheduling algorithm, that can be implemented or used in a real system. Okay? So we can call that as an instance of this general approach. So here, for example, we can give an instance, a specific algorithm derived from this general idea. So in this specific instance, in this specific algorithm, we can say that we will have just three queues, Q0, Q1, Q2. Q0 will be served with round robin, where the time quantum is 8 milliseconds. Q1 will be served with round robin again, but the time quantum will be 16 milliseconds, okay? And Q2 will be served with FCFS. That means the Q2 should include the processes that are not interactive, that are behaving like batch process, okay? But initially we may not know when the process is created whether that process will behave as an interactive process or as a batch process running in the background, okay? But when the process is executing, we can derive an estimation about how the process is behaving, okay? We can learn about it. So how do we learn about that? Initially, when a new job is created, okay, it will be put into the Q0. Q0 is a queue which is served with round robin. That means the interactive processes should be staying there. Similarly, Q1 can include the interactive process, but in Q1 we have a time quantum set to 60 milliseconds. That means more CPU-bound processes, interactive processes, should be put into Q1, because when they are scheduled, they will use the CPU more, okay? Because in Q1 we are giving more time quantum. That means such a process that will require the CPU more should be staying there. But a process that is heavily interacting with the user, which is not doing much computation, that means it needs actually very small time slice, time quantum. Once it's given the CPU, it will not stay there. It will immediately start interacting with the user or with the disk and so on. Such an IO-bound process should have a very high priority because it is interacting with the user. Therefore, it should stay in Q0. So Q0 has the highest priority, Q1 has the next highest priority, and Q2 has the lowest priority. So an interactive process that is interacting with the user should be having the highest priority, should be here. Such a process usually do not do much computing, right, in the CPU. Once given the CPU, it runs there for a very short amount of time, maybe just 2 seconds, so it will not be able to expire its time quantum. And then immediately will start its I/O with the user, okay? So it is good to have those processes here. They will have highest priorities because they need to use the CPU immediately. The response time for them should be very small, because when such a process is to be using the CPU should be given to that process in a short amount of time because there is a user waiting for an output from that process. Yes?
If a process in Q0, when it is dispatched, it blocks after 3 milliseconds, for example.
Right, right.
Does it stay
yes.
Q0 afterwards?
Yes, yes. Exactly. So this is the rule that we have specified. So this algorithm, yes, according to this algorithm that is specified here, the process, if it cannot expire its time quantum, it should stay in the same queue. So what happens, for example, a process enters here, is considered a highest priority job, but the system observes that whether the process expires its time quantum or not. So when the process is given the CPU, okay, if it stays in the CPU for more than 8 milliseconds, of course it cannot, but if it expires its time quantum, then it is moved to the next queue because the system considers it to be a little bit CPU bound process. It can still be interactive, but it is more CPU bound than the process here, so it is moved to second queue, okay? So a new job enters Q0, which is served with round robin, but when it gains the CPU, if it receives 8 milliseconds CPU and it exhausts its time slice, that means if it doesn't finish in 8 milliseconds, then it is moved to second queue, okay? So then a job in the second queue can be assigned to CPU, it can run there. Again, the system observes whether the process exhausts its time slice or not, expires it. If it expires, that means if it does not finish before 60 milliseconds, okay, during its time quantum, then again that process is considered a CPU bound foreground, a background process, and it is moved to third queue, okay, Q2. So at Q1, job is again served at Q1. Job is served with round robin and receives 16 additional milliseconds. And if it still doesn't complete, then it is preempted and moved to Q2. Okay. So these are the rules here. While specifying an algorithm, multi-level feedback queue algorithm, you have to specify the number of queues, how the process is changed between the queues, and so on. So this is an example which specifies the rules that are used to change the queues that a process is assigned.
Is there an algorithm between queues?
Yes, the algorithm is strict priority-based scheduling. As long as there are processes here, the system runs those processes, okay? So this has the highest priority. If we have some process here, the system will run them, okay? Hopefully we will not have that much processes there because they are very I/O-bound processes. They will immediately start their I/O operation. They will run in the CPU for a small amount of time, and then they will go and do keyboard I/O for 5 seconds. They will not appear in the ready queue, okay? So hopefully we will not have starvation, yes.
Is it also logical to move an operation which takes less than 8 milliseconds and which resides in Q1 and move it to Q0 when it takes less than 8 milliseconds?
Yes, this algorithm is not specifying that, but why not? We can do that also. So this algorithm, for example, that's described in the book, is not specifying how to promote the processes, how to increase their priorities again. But why not? We can do that. Or we can have such a rule, for example, after a process stays here for a while, it will be again moved to Q0, and then it can start sinking down, okay? Any questions? All right. So far we have talked about the scheduling algorithms that can be used for processes. Same algorithms can be used for thread scheduling. There is not much difference between thread scheduling and process scheduling, okay? The same ideas apply. And those algorithms are basically, that we have described, are basic approach. A real system like Linux, Windows, or a system that is running a web server, okay, is using an algorithm, a real algorithm that actually borrows from these ideas, okay? So Linux is using, for example, priority-based scheduling together with multi-level queues, where the priorities are dynamic, and inside each queue we are serving the processes using round robin and so on, okay? So a real scheduler is using these ideas, combining them in a different, in a unique way, and it's a unique scheduling algorithm that's implemented in a system, all right? So we are not using these ideas alone, like, for example, a real system is not using just FCFS idea or round-robin idea, but it's combining many ideas together to implement a real scheduler, okay? So thread scheduling is nearly the same thing. In Unix, actually, there is not much difference between the threads and processes. Each are schedulable entities, okay? So you consider a thread like a process and schedule them. So when a thread has consumed quite a lot of time, then you suspend it and schedule another thread, okay? So the basic idea is the same, scheduling for the threads is the same, but you can also do something else with the threads. So sometimes you may want to make a distinction. So, for example, in too many model systems where you can create some number of kernel threads and you can create lots of user level threads, okay, that are mapped into those kernel level threads. You can specify or in two-level model where you can have also some threads that are mapped directly to the kernel level threads, right? You can have, for example, you can specify as the application programmer, whenever you create a thread, whether that thread will be scheduled by the thread library as part of that process or by the kernel and so on. So if you are actually scheduling the threads as part of that process at the user level, that means that you are scheduling in process contention scope. Okay? If you are actually using the kernel to schedule the threads, then that means you are using system contention scope to schedule the threads. Okay? So then we are having competition among all the threads in the system for scheduling. Otherwise, we are having competition among the threads of that single process, okay, while doing the scheduling. So you can specify actually which scheduling will be used using an API function. The pthreads API function, there is a pthread API function that enables you to do that. That function is called, for example, pthread attribute set scope. With that, before creating threads, you can call that function. Basically, remember the attribute variable that we can define. We can get the default values for that using the pthread attribute init function. You can obtain, for example, the default values, attribute values for threads into a variable that you define. Okay, then you can change the default values. For the scheduling, whether kernel level scheduling or user level scheduling will be applied, you have a default value. But you can change that by using this function, pthread attribute set scope. For example, here, this example is setting the scope to system. That means the system, the kernel will schedule the thread among all the threads that it sees. Okay? Then you can also specify the scheduling policy for that thread. So that thread may be running a real-time application. Or that thread may be an ordinary process thread, doing some ordinary activity like editing or like, for example, compiling. Okay? Or that thread may be, for example, just doing number crunching, running in the background. Okay? So then you can set actually the policy, scheduling policy for that thread. For example, scheduling other means that that thread is actually an ordinary process or will be an ordinary thread, like editing something like an interactive process. Okay? But you can also specify, for example, the thread to be scheduled using FCFS. So if it's a batch process, then you can specify the policy to be FIFO. If it's a real-time thread running a real-time task, then you can specify the scheduling policy to be real-time. Okay, this is possible. Then the kernel will assign a higher priority to that thread. If you have specified, for example, scheduling RT here, okay, as scheduling policy to be applied to that thread, if you specify that the kernel will treat that thread as a higher priority thread. Any questions so far? Okay, then there is not much difference between the threads and process in terms of scheduling. Now let's look to multiprocessor scheduling a little bit. So far we have seen the single processor scheduling. Okay, what will happen in a multiprocessor environment, which is common today, right? So in a multiprocessor environment, we have several CPUs, and CPU scheduling becomes more complex when multiple CPUs are available in a single computer. So these CPUs actually can be working as asymmetric multiprocessing or symmetric multiprocessing. In an asymmetric multiprocessing environment or architecture, what we have is we have just one single CPU running the system code, doing the scheduling and so on. So even though, for example, we may have 4 processors, only one of them is acting as the master processor, which is running the kernel code, system code, the scheduler, okay, controlling the scheduling queue, ready queue, and so on. So it makes the scheduling decisions. Okay, the system code is running there, scheduling the processes to other 3 available processors. Okay, but in symmetric multiprocessing, we do not have a special master processor. Each 4 processors have equal responsibility. They can run kernel code and user level code. Okay, therefore each of them is self-scheduling. Each processor run the kernel code, kernel scheduler separately. Each may have its own ready queue. All right. So each processor is running the system code, scheduler its own scheduler, and scheduling the processes in its ready queue, independent of the other schedulers running in other CPUs. Okay. So this is the symmetric multiprocessing, and or desktop computers, PCs operate usually in this manner. Okay, they are symmetric machines. We have symmetric CPUs, dual core machines, quad core machines are symmetric multiprocessing machines where each processor is self-scheduling all processes can be in a common ready queue, or most of the time each processor has its own ready queue. Then each processor runs its own scheduling algorithm to schedule the processes in their ready queues. Okay. However, the kernel can sometimes move the one process from this ready queue to another ready queue, from one processor to another processor. But this is not a desirable thing to do, because once a process starts running in one CPU, that CPU has its own memory cache, which is populated with the data and instructions of that process, right? So if you switch that process to another CPU, then you have to invalidate that cache and repopulate the other cache in the other CPU, which is overhead, right? So you usually do not want to do that, and the kernel usually tries to not to do that. This is called soft affinity. So the process has affinity to the processor on which it is started on. Okay? So the kernel tries to leave that process on that processor. But the kernel doesn't guarantee to do that. Sometimes it may move this process from this processor to another processor. Okay? Maybe the other processor is idle for a long amount of time and this processor is too loaded, so the kernel may move the process from one processor to another processor, but it tries to keep the affinity. This is called soft affinity. If, however, the kernel guarantees, okay, you can specify at the process creation time that you would like to be bound to a CPU processor, to a processor, and you will stay there for your whole lifetime. The kernel will never move you to a different processor. If this is guaranteed, then that means we are applying hard affinity. And you can specify for your process which one should be applied, okay? And also we have different architectures. We have also architectures where we have multiple CPUs in a system. We have multiple boards, CPU boards. In one board we have CPU and also some amount of memory, local memory. And in another board, again, we have some CPU and some amount of local memory, so that these local memories can be accessed by CPU. So this CPU can access this local memory, but it can also access that local memory, okay? But accessing this is fast, accessing that is a little bit slower because you are accessing a different board, right? So now the kernel may be aware of that and make the scheduling and memory allocation depending on this architecture and considering this architecture. What does it imply is when a process is scheduled to use that CPU, right? The kernel should also make the memory allocations for that process from this memory. It should try to do that, okay? If it would like to provide good performance, then the memory allocated to that process should be not from that, if possible, but from this memory, okay? Of course, if this is filled up, then we can go ahead and allocate some memory from this memory to that process running here, but we should try to avoid that, okay, in those architectures which are called NUMA architectures, okay, non-uniform memory access architectures. So nowadays we have multi-core processors, and in these multi-core processors we can have a thread or process run in one processor, another thread in another processor, and so on. Even though we have a single processor, okay, single core, then what we can, the hardware, what it can do is it can actually provide the illusion that there are multiple cores. This is called hypertrading, okay, hardware trading. So multiple threads per core can be provided by the hardware. For example, at least 2 threads can be provided by the hardware. What does it mean? That means, for example, if you look to the behavior of one thread or process, what happens is that it executes instructions, but while executing the instructions, it actually takes the operands from the memory. But taking the operand from the memory takes time compared to taking the operand from the registers, right? But you have to take the operands from the memory. So when you look to the behavior of the process, what it is doing, it is actually doing arithmetic operations and so on, but also going to the memory and taking something, okay? So it is doing some computing, plus going to memory and retrieving the operands or storing the operands, then computing, then going to the memory, then computing, and so on, right? So what we can do now, we can have a single arithmetic logic unit, single processing unit, But we can have two set of registers and so on to implement two threads now as part of the same CPU, okay? So that while one thread is computing here, another thread may go and retrieve the operands from the memory. And then it can compute, and this thread may go and retrieve the operands from the memory, okay? In this way, you are utilizing the CPU and memory in a better way. Otherwise, while this thread has computed, it has to wait for the operands to be available. During this time, it will not compute, and so on, right? The ALU will be not busy during this time. But with this hypertrading, okay, hardware trading, now you are utilizing the components in a much better way. And this is done completely by hardware. So the operating system now sees such a CPU, such a single core machine. It sees it to be actually two CPUs, right? It can execute it can create two threads and run them on the same CPU, okay? In a hardware parallel manner. Any questions here? So now let's look to some operating system examples very briefly. And we will not look to Solaris and Windows XP scheduling, so you can read them from the book. We will briefly look to the Linux scheduling, okay? So Linux scheduler works in O1 time. What does it mean? It makes the scheduling decisions in O1 time. Constant amount of time the scheduling decision is given. Basically, the next process to use the CPU is selected in a constant amount of time, no matter what the size of the ready queue is, okay? It can be having 10 processes or 200 processes, okay? The scheduling decision is given in a constant amount of time. So it is independent. The amount of time that you spend to make the scheduling decision is independent of the size of the ready queue, okay? So therefore we say it's O1 scheduler. So it uses priority-based scheduling, it uses round-robin, it uses multiple-level queues, and so on, okay? It can also change the priorities of the processes, so processes have static priority, but also dynamic priority, okay? So it uses actually, it combines the ideas that we have seen so far to make a scheduler, all right? So there are two priority ranges. Real-time processes have a different range that is higher priority than normal ordinary processes, time-sharing processes, okay? So we have a range of priorities that can be assigned to real-time processes and a range of priorities that can be assigned to ordinary tasks that we can create, like the Word, Excel programs, or the compilers, and so on, okay? So the real-time priority range changes from 0 to 99. In Linux, we use lower numbers to represent higher priorities, okay? So 0 is the highest priority. So real-time range changes from 0 to 99, okay? And we have the ordinary processes assigned priorities changing from 0 to 140, okay? So we have such a range of priorities shared by the processes. So this priority range belongs to the real-time tasks, and that priority range is used by other tasks, the normal tasks that we are using. Therefore, it is, if you are using scheduling other for your thread that you have created, that means you are actually considering it as an ordinary process who has to be assigned a priority in that range, okay? So now in Linux, as I said, a lower priority number is given to the highest process, okay? So the highest priority process has the lowest number. So, and also the highest priority processes, or the higher the priority of a process, the larger the time quantum assigned to that process, okay? So a very lowest priority process is assigned a time quantum 10 milliseconds. A very high priority process is assigned a time quantum close to 200 milliseconds. What does it mean? It means the process can run at most that much of time in the CPU, right? Then when that has expired, it has to be stopped, suspended, until all other processes in the system has chance of using the CPU at least once. Okay? So you will understand what it means with this example that we are giving here. So as we said, we have priorities for the tasks. So priority range changes from 0 to 140. So for each priority, we have a set of processes in that priority, right? So we have a priority array here. So in each array entry, we have a task list. So assume we have 2 processes here in that priority, 3 processes in that priority, 1 process in that priority, and so on. So the these different queues or priority levels are served in a strict priority manner, meaning that if there is a process here at the highest priority, it is run always, okay? As long as there are processes here, they are run. You don't go and run here when there are processes here. But there is a limit that these processes can run, which is the time quantum. So as I said, here, for such processes at the highest level, that time quantum is 200 milliseconds. So you can run this for a while, 10 milliseconds, and then 10 milliseconds this, 10 milliseconds, 10 milliseconds, and so on. Sooner or later, this will be running a total amount of 200 milliseconds in the CPU, right? Then it can no longer run. It is moved to here, which is called expired array of queues. Expired means that it has expired its time quantum. It had a quite long time quantum. It did not use it in one shot, okay? It used it for a while, and then another highest priority process is run, and so on. But sooner or later, the time quantum of these processes has expired, and they are moved there. So you will no longer have those processes hogging the CPU all the time. So therefore, starvation is prevented. They will run more for a long time, but not all the time, okay? Then you go and schedule the process from there. So you apply strict priority scheduling among the queues. As long as there are processes in the higher priority queue, you run the process there. But sooner or later, they will expire their time quantums and they will be moved to here. And therefore, all the processes here will have a chance to use the CPU, okay? And as a result, at the end, what you will have? You will have all the processes here expired their time quantums and moved to here, okay? Then this becomes your active array, and you start scheduling processes from there. That means, again, this process has a chance of now using the CPU. After all these processes have used the CPU for a while, okay? This is how the UNIX scheduler is operating, okay? So it is using the round-robin idea. It is based on priority scheduling. Also, the priorities of the processes may change. You can start with a priority, let's say 130. But depending on your activity level, if you are sleeping more, your priority is increased. If you are sleeping less, your priority is decreased. If you are a keyboard-oriented process, waiting lots of inputs from the keyboard, that means you are sleeping more and your priority is increased. Therefore, that means you will have a bigger time quantum and also higher priority, which means that you will have a shorter response time. You will wait less until your next CPU service compared to other lower priority processes, okay? But if you are actually not sleeping much, doing lots of computation, that means you are not much an interactive process, your priority will be decreased. And therefore, your response time will be decreased as well, and so on, okay? This is how Linux scheduler is operating. Any questions here? Yes?
What happens when you're executing a task in the third queue? A new task enters at the first queue, for example?
Yes, immediately you jump to the first queue, you start executing, yes. So Linux is using preemptive scheduling, okay? All right, so now assume you have several algorithms as the scheduling algorithms. What is the method that you can use to evaluate those algorithms, to judge at the end whether this algorithm is better or that algorithm is better, and so on? We know some evaluation criteria, right? We have seen some evaluation criteria, like, for example, the average turnaround time, or the average waiting time, or the response time, or the CPU utilization. So what is the method that you can use to evaluate several algorithms using those evaluation criteria? So what are the methods? One method is deterministic modeling that we have already done, right? We have, there was a Gantt chart that we have used, right? Given a set of processes with their CPU types and so on. In that Gantt chart, we specified, for example, the order of execution of the processes depending on the scheduling algorithm that's given. And then we derived a metric value, like, for example, average turnaround time and so on, or average waiting time, right? So we can use such a Gantt chart and so on. This is called deterministic modeling. Here, the scenario is deterministic. You have the set of processes and specific CPU times assigned to them, and you run your algorithm against this specific scenario and obtain a metric value and judge which algorithm is better according to that metric, okay? So it takes a particular predetermined workload, set of processes and their CPU times, and defines the performance of each algorithm using a metric like average waiting time and so on for that workload only, okay? So this is deterministic modeling. So this is something that we can use, all right? But here, actually, the number of processes and their CPU times is deterministic, and this may not reflect the reality. In reality, we don't know the exact CPU time required by the processes. We may know maybe their distributions and so on. So what you can do is you can actually use simulation as a better approach. You can simulate the algorithms, okay? You can enter your workload into a file, okay, where each process, the process will have this CPU burst and then this IO burst and so on. So this can be the behavior of one process, another process, and so on. So you can give this as an input to your simulation, which is implementing various scheduling algorithms, and then providing you at the end of the simulation the performance metrics, like, for example, what's the average waiting time for each algorithm, okay? So you can write a simulation program in Java or C++ and so on. You can simulate the processor behavior using this workload. That Java program that you are writing will simulate the execution of the processes with a scheduling algorithm, and then will print out the metric values, and in this way you will be able to judge which algorithm is better against which other one. And now also you can here use deterministic workloads, but also you can actually generate these numbers here in a random manner, okay? Using random numbers according to some probability distributions, you can generate those numbers. So you can generate any process with some CPU time requirement as a random number, okay? Execute that, and then generate another process with some CPU requirement and so on. So the workload can be generated in this way as well, okay? So this is another method, simulation. And another method is the queuing models. So mathematic models can be used. There is a branch of research called queuing theory, okay? Where, for example, assuming some distributions for the CPU burst lengths, process CPU times, the distribution can be exponential, for example, all right? And assuming a distribution for the interarrival times between the processes. A process arrives to the ready queue, and then the next process arrives after some time later, and another process arrives after some time later. So that time interval is not deterministic, right? But we can assume a probability distribution for that. Let's say we can say that it is exponentially distributed, right? So based on these assumed distributions, okay, people has worked on some results, mathematical results, that, for example, relates the average waiting time in the queue, all right, and the average interarrival time, average service rate. If they are given, there's a formula expressing, for example, how much time each process will wait, what will be the queue length, average queue length will be, and so on. If you know the, for example, average service rate, the CPU power, if you know the average arrival rate for the process and so on, then using those mathematical models, you have some formulas which relate the average queue length and average waiting time on the queue to the arrival rate and the service rate and so on, okay? So this is the queuing model approach. You can use those mathematical models to have an idea about the performance of a scheduling algorithm. And the last method is implementation. You can just implement the scheduling algorithm in a real system. In the Linux kernel, for example, you can just go ahead and modify the Linux scheduler with your own scheduling algorithm if you wish. Then you can see how the system behaves, evaluate that, okay? So of course this is quite difficult. You have to touch the kernel, modify it, and so on. And also you have to find people to evaluate your system and so on. But this is another way to evaluate the algorithms. It may be better in some cases because now actually you are implementing it in a real system, not simulation and so on. But it may be more difficult. So these are the methods that we can use to evaluate various algorithms that are designed as scheduling algorithms. Okay, any questions? So this is the end of the lecture, which is the end of chapter 5. Okay, and next week we will start with chapter 6, which will be the process synchronization. So there we will learn how we can actually synchronize or coordinate the activities of various processes, which will be important, for example, especially when those processes are actually sharing a variable or sharing data, okay, and manipulating the shared data. Okay, so we can stop here.